In this video, we're going to begin Chapter 3 on applications of differentiation. In order to be able to handle the concepts in this chapter, you're going to have to be very confident and familiar with the derivative rules that we covered in Chapter 2, because you will be using those within application problems throughout this chapter. So this first section is section 3.1 on using the first derivatives to find maximum and minimum values and sketch graphs. So basically learning how the derivative, what the derivative function tells you about the shape of a graph. So our objectives here are to find relative extrema, meaning maxes and mins, of a continuous function using the first derivative, and to be able to sketch graphs of continuous functions. We'll be using your graphing calculator will be a big help here when you're asked to kind of look at what you found with the derivative and use it to help you sketch a graph. So our first definition is using the first derivative to figure out where a function is increasing and decreasing. So we're going to first define what that means. So a function f is considered to be increasing over an interval I if, for every a and b in the interval, if a is less than b, meaning a comes before b, then f of a is less than f of b. In other words, if the x value is smaller, then the y value is smaller. So if the input is less than if the input A is less than the input B, then the output for A is less than the output for B. If that is true all the way through the interval, that means your graph would be moving upward as you read it from left to right, or increasing. A function f is decreasing over I if for every A and B in the interval, if A comes before B, or A is less than B, then f of A is greater than f of B. So in other words, if the input A is less than the input B, then the output for A is greater than the output for B. So in other words, for a smaller x value, the output is higher than it is for a larger x value. That would mean the graph would be moving downward as you look at it from left to right. We're going to be talking about increasing and decreasing in terms of derivative values and also just by more of a visual looking at the graph. All right, so theorem number 1 talks about what the derivative means in each of those cases. Let f be differentiable over some open interval I. If f prime of x is greater than 0, meaning that the first derivative is positive for all x in the interval, that would indicate that f, the function, is increasing. So first derivative value being positive, greater than 0, means that the function is increasing. If the first derivative value is less than 0, meaning it's negative, first derivative being a negative value for all x, then the function will be decreasing. All right. We're going to be having to identify what we call critical values. So the definition of a critical value of a function, f, is any number c in the domain of f for which the tangent line at the x value c, y value f of c is horizontal, meaning that the slope is 0. Tangent line being horizontal means the slope of that tangent line is 0, or for which the derivative just does not exist. So in other words, c is a critical value if f of c exists, the function, and the derivative either equals 0, meaning that your slope of your tangent, if your tangent line is horizontal, means that slope is 0. So the derivative, remember, is the slope of the tangent line. So f prime of c is 0 or f prime of c does not exist. So if we can find f prime, we can figure out the values of c for which either of these occur, we can find critical values. So if you find a critical value c, then the point c f of c is called a critical point. So the critical value is just the value of c. The critical point is the ordered pair. All right. Some more definitions of maximums and minimums. Let I be in the domain of the function f. F of c is a relative minimum if there exists within an interval I1 containing C such that f of C is less than or equal to f of x for all x in I. So a relative minimum is kind of like the bottom of a parabola, or like if you have a cubic function that kind of goes up and down, it's kind of the bottom of a hill within a smaller subset of the domain. The word relative means it might not be the lowest value overall, but it is a small value within a smaller subset. F of C is a relative max if there exists within I an open interval I2, so a subset of the domain containing the C value right here, such that f of C is greater than or equal to f of x for all x in I2. In other words, it's kind of like the top of a hill, like if the parabola graph was upside down and it had a high point, or if you had a lot of those similar features on your graph throughout the domain, those would be relative maximums. And then our second theorem says a function f has a relative extreme value f of C on an open interval, then C is a critical value. So in other words, f prime of C equals 0 or f prime of C does not exist. So those maxes and mins, the possible locations for where they would occur, if that's what you're looking to find, are at the critical values. So our procedure here is going to be first locate the critical values by using the derivative, and then we'll have ways of deciding if they're maximums or minimums. All right, so theorem 3 is called the first derivative test for relative extrema. So for any continuous function f that has exactly one critical value, C, in an open interval, F1 says f has a relative minimum at C if f prime of x less than 0 on the interval from A to C, so from the beginning of the interval up to C. In other words, that the function, notice this says that f prime less than 0, we talked about earlier, says that the function is decreasing, and then f prime of C greater than 0 would mean the function is increasing from C to B. So in other words, if the function is moving down on the left of C and then moving up on the right of C, then it would have to hit a minimum in between. Imagine a function going downward, moving down, being decreasing, then turning around and being increasing. The point where it turns around would have to then be a min. So it has a relative min if the derivative is negative on the left of C and the derivative is positive on the right. So it's decreasing to the left and increasing to the right. F has a relative max if f prime is greater than 0 on the left of C, in other words from A up to C, and f prime is less than 0 from C to B, or other words on the right. So this first derivative positive means increasing, moving upward, and then f prime less than 0 means then moving down. So if it goes up, then it turns around and comes down, it would have to hit a max at that spot. So f would be increasing to the left and decreasing to the right. And then f has neither a relative max nor a relative min at C if f prime has the same sign on the left and the right. So if it's moving upward, and then maybe it flattens off to have a horizontal slope, but then it still goes up on the other side, there's no max or min. Or if it was coming down, and then it stays coming down, in other words, decreasing, decreasing, or increasing, increasing, it's not going to change direction, then it's not going to have a max or a min. So critical values could indicate a max or a min, depending on the pattern of does it increase, decrease, or vice versa, or it could be neither. It doesn't have to have a max or a min there. So here's the visual. This is a little bit easier to understand, I think. All right, so if the graph over the interval A to B looks like this, so in other words, notice here that if I drew in a tangent line, it would have a negative slope, meaning that the function is decreasing, meaning that my slope is negative up to here. Then it would have a horizontal tangent, meaning that the slope would become 0. But then on the other side, notice that when it's increasing, any tangent line I draw would have a positive slope. So if it goes from decreasing to increasing, in other words, a negative derivative to a positive derivative, we have to hit a min. So the sign for f prime between A and C is negative, meaning the slope of the tangent line is negative. The sign for f prime from c to b, positive, meaning that the slope of the tangent line is positive. So the derivative sign changes from decrease to increase, or negative to positive. Then we have a relative min. In the other case, this would be an increasing section of my graph. Notice that a tangent line here would have a positive slope. So the sign of f prime would be positive between a and c. Then it would hit my 0, a flat tangent line right here. That's where the critical point occurs. And then a negative slope when it turns around to be a decreasing section of the graph. So the sign for f prime being negative after between c and b. So it increases first, then decreases, means you have to hit a max in the middle. Okay, this is probably the most useful slide so far, just to kind of see it all summarized and have the visual picture. All right, here's the examples of if it didn't change sign. So what could happen? You could have a decreasing or negative slope. It could flatten off to have a 0 slope here, where that would have been a critical point, but then it could continue to decrease with a negative slope. So notice that there is no relative max or min if they have the same, if the derivative has the same sign on either side. So it's decreasing the entire way, or if it were increasing the entire way. Increasing with a positive tangent line slope, and then maybe hitting a 0 slope here for a critical point, but continuing to increase with a positive slope, no max or min happens. So if it doesn't change sign at the critical point in terms of the derivative, there is no max or min. All right, so our first example, graph the function given by this cubic polynomial and find relative extrema, meaning maxes and mins. So our first step is going to be find the derivative. All right, so here, suppose we're trying to graph this function, but if we don't know any calculus at all, what would you do? Well, you'd plot a few points and determine which direction the graph seems to be turning, right? Just plot a bunch of points and connect the dots. So they're going to start this first example that way, so we can kind of get a visual of what the graph looks like to help make sense of our derivatives. All right, so they just picked a bunch of x's, plugged them into that function with your calculator, got a bunch of y values, and then showed what the graphs look like. So this would be much faster to do this using a graphing calculator without having to make a table. So knowing how to plug your function into your calculator, get a decent window. Notice that the window here in the x direction is -5 to 6, but in the y direction they've had to alter it to be larger values. So you have to play around with your window to get this to show up. But if you put it into your calculator and adjusted your window accordingly, it would help you kind of see what's going on here, or making a table of a bunch of numbers. So they plotted some points here and seen that the pattern shows this shape. So if we notice here, it looks like about this spot right here, my slope looks like it would be 0, so that should be a critical point. And notice again over here, so this looks like on my graph would indicate a relative max. And right here, this would also look like a critical point where the slope would be flat of the tangent line, and this would be indication of a relative min. Okay, so we're going to try to verify with our derivative rules if that's actually what happens. All right, so we can see some features of the graph from the sketch. Now we'll calculate the coordinates precisely to get exactly where they're located. So step 1, find a general expression for the derivative. So just taking the derivative of that function would give me 6x squared minus 6x minus 12. Determine where that first derivative does not exist or where the first derivative equals 0. Those are the possible locations of critical points. Now, since f prime is a polynomial, meaning that all the powers are positive integer exponents, then there's no value where this doesn't exist. In other words, there's no x that I could plug in to give me an undefined result. So there's no possibility of f prime not existing. So there's only possibilities for critical values or where it's going to equal 0. All right, so we'll set it equal to 0. That was my derivative function. Set it equal to 0. Here we just divided everything by 6 to make the number smaller, because everything's divisible by 6. Then we factor, so that can be solved by factoring. factor, and then set each factor to 0 gives me critical values of 2 and -1. So at x equals 2 and x equals -1 are the possible locations for maxes and mins. All right, so if I take these two values and partition them into the number line in 3 intervals. So if I draw a number line, I plot those points -1 and 2. So I have interval A from -infinity up to -1, interval B from -1 to 2, and then interval C from 2 to infinity. Okay, so on the left of -1, it's either increasing or decreasing. On the in the middle, it's either increasing or decreasing, and then to the right, it's either increasing or decreasing. All right, next we're going to analyze the sign of f prime in each of those intervals. So our table here means I'm going to pick a test value in interval A. So if this is at -1, any value of x over here can be a test value. So they've chosen -2. B is the interval between -1 and 2. So pick a number that lands in that space. They've chosen 0. And then for the third space between 2 and infinity, pick any x value that lands here. So they picked 4. So they've chosen the test values within each space. Then we're going to look at the sign of f prime. We want to know if f prime is positive or negative to know if it increases and then decreases or vice versa. All right, so if I were to plug -2 into f prime, so in other words, if you evaluate the f prime function by plugging in -2, we get a positive number. When I plug in 0 into f prime, we get a negative number. And if we plug 4 into f prime, we get a positive number. So hopefully you wrote down what f prime was as you're taking notes, or if you have it on the printout. Those values are coming from plugging each of those test values into the derivative function. Okay, so since f prime is positive, this means that f should be increasing. First derivative positive means f is increasing on this interval from -infinity up to -1. Since we got a negative value here, that means f, the function, is derivative being negative means decreasing from -1 to 2. And then in the third interval, we got positive for the derivative, meaning that the function is increasing from 2 to infinity. So that means if I was graphing without having drawn it to start, you would move up until you got to -1 as an x value, then it would go down until you got to the +2 as an x, and then up again. All right, so by the first derivative test, f would have a relative max at -1. So let's go back here. Why would it have a relative max at -1? Here was our critical point. This interval we said was increasing and then decrease. So it would go increase to decrease. So it would have to hit a max where it turned around. Here the sign change on either side of 2 was negative to positive, meaning decrease to increase. So if it was decreasing up to here and then increasing on the other side, that would have to have a min. Okay, so that's where this is coming from. F has a max at -1 because it went increase to decrease. So to find the ordered pair, we plug -1 into the function to get 19. That would be that point on the actual graph. So -1, 19 is a relative max. F has relative min at 2 because of the decrease to increase pattern in the chart on either side of 2. So if I plug 2 into my function, I get -8. So that means that the ordered pair 2, -8 would be your relative min, which is what we saw on the initial graph. This is just verifying it or figuring it out if you were not able to sketch a graph first. All right, so let's try another one here. Graph the function given by this cubic and find the relative extrema. Okay. All right, so if we graph this on the calculator, again, you'd have to play around with your window, plug it into your calculator, and then mess with your window. This shows a like -100 to 100 y window, maybe like a -5 to 5 or a -6 to 6 x window. So you'll have to kind of adjust that to see exactly this picture. So it looks like about right here, maybe at -3, we've got a relative max. And then over here, maybe around positive 3, looks like we have a relative min. And our function should be increasing, then decreasing, and then increasing in those other spaces. So let's see if we can verify. All right, so it looks like negative 3, they've probably used a calculator to find that this is at 48, and then positive 3 down here at negative 60. Now, I don't think they're gonna, I think they maybe are just doing this one by the calculator, but you could go through and find your first derivative, 3x squared minus 27, set it to 0 to get your critical values of negative 3 and 3, do the chart like they did on the last example. You should get, plugging in a number on the left of negative 3 into the derivative should be positive, plugging in something in between should be negative, and something on the other side should be positive. And then plugging negative 3 and positive 3 back into the function should give you the 48 and the negative 60. All right, so here we're going to do it without necessarily just using a graph. So for the function given by this equation, find the relative extrema, meaning maxes and mins. Then sketch a graph. So we'll do the calculus part first, and then we'll look at the graph to see if it makes sense. So first find f prime. So power rule, 2/3 x minus 2, subtract 1 from 2/3 gives me negative 1/3. The function on the inside, its derivative is 1. All right, so the chain rule part there just would multiply by 1, so that would just be it. We rewrote this with this negative moving this whole factor then to the denominator to make it a positive 1/3, and the 1/3 power is the cubed root. Then we're going to find where f prime does not exist, or where f prime is equal to 0. So this time, notice f prime does not exist anywhere where the denominator is 0. So this function's derivative had something in the denominator. So since the denominator, if you set the denominator equal to 0, that happens when x is 2, then x equals 2 is a critical value. I'll go back to show you real quick where that's coming from, right here. This denominator, if I set to 0 when x is 2, makes the bottom 0, so that means 2 would be a critical value, because that would mean the derivative doesn't exist. All right, f prime equals 0 when the numerator is 0, but since this function, the numerator is always 2, right? So it's never going to equal 0, so there's no solution for setting the whole thing to 0. So the only critical value we have here is 2. You could get critical values from setting the bottom to 0, could get critical values from setting the top. You could have some that come from either, or you could have, none. But you have to look at both situations. All right, next we're going to take that our one critical value means our number line, our interval gets split into 2 pieces. So negative infinity up to 2 is our first one, and then 2 to infinity is the second one. So we're going to look at the sign of f prime in both of those spaces. So they've chosen a number over here, they picked 0, and then they picked a number over in this space, 3. So when you plug into the derivative function, if you plug a 0 in, we get a negative number. And if you plug in 3 into the derivative, you get a positive number. So if the derivative is negative, f is decreasing on that interval, negative infinity up to 2. And if the derivative is positive, f is increasing, and that would be on the interval from 2 to infinity. Therefore, by first derivative test, f has a relative minimum. Remember, because decrease to increase, right, means going down and then coming up would have to give you a min. F has relative min at 2, so you plug 2 into the original function to get that ordered pair. So if I plug it into the original function f of 2, we get 1. So the ordered pair 2, 1 would be a relative min. All right, so then if you made a table or use your calculator to sketch the graph, if you type this into your calculator, this window is a little easier probably to find because it's just some smaller values than the standard. See, it's decreasing, to here, and then it turns around and increases over here. So this would indicate a relative min. So that would agree with the graph. All right, so let's try to do another one here. Find the relative extreme of the function h given by this equation, and then sketch the graph. So first we're going to find the derivative. Derivative 4x cubed minus the 8/3 just stays there, and then you do 3x squared by the power rule. Cleaning that up gives me 4x cubed minus 8x squared. Oops. Okay. 4x cubed minus 3x squared because your 3, or 8x squared because your 3's cancel. All right, next find where h prime doesn't exist or where it equals 0. That's the critical points. So h prime equals 0. It would never not exist, right? So the only thing we're worried about here is when it equals 0. So here we can factor out of 4x squared, leaving x minus 2. And then setting this to 0 gives me 0, and setting this to 0 gives me 2. So when x is 0 or x is 2. Thus, 0 and 2 are my critical values. All right. Next, we're going to take x equals 0 and x equal 2, partition the number line into 3 intervals. The first one going negative infinity to 0, meaning on the left of the 0, then in between the 2, between 0 and 2, and then to the right of 2. And then we're going to look at the sign of the derivative in all 3. All right, so in interval A, pick a test value that's between negative infinity and 0. So like negative 2. In B, we're going to pick a test value in between 0 and 2, so let's pick 1. And then C, pick a test value between 2 and infinity, so 3. So plugging each of those x's into the derivative gives me a negative value when I plug negative 2 in, still a negative value if I plug in a 1, and then a positive value if I plug in a 3. Meaning, negative derivative means the function is decreasing. Still decreasing. Then increasing for the positive. So notice there's no sign change here. Decrease, decrease. So that breaking point between the two intervals A and B, which was 0, there would be no max or min. Then it went decrease to increase between B and C. So between B and C, which was at 2, it went decrease to increase. So that should be a min. Okay, so there's a min at 2. So plugging 2 back into the function, the original function would give you negative 16/3. That would be the ordered pair of the minimum. All right, and then you can graph on your calculator. Notice there's a critical value at 0 because there's a slope of tangent line at 0 here, but it was decrease, still decrease. That's not a max or a min. Here's your min, right, at the 2, negative 16/3, right? So that would agree with what our derivatives told us. All right. Next one, find the relative extreme of the function given by 3 minus x to the 1/3, then sketch the graph. All right, again, first derivative, negative 1/3 x, subtract 1 from the power, gives me, this power would become negative 2/3, so they've just moved that to the denominator to make it a positive 2/3. Second, find where it either doesn't exist or equals 0. So g prime does not exist when the denominator equals 0, so g prime won't exist at 0. And then there's no value that makes it equal 0. So the denominator is where the variable was located, so that's where this comes from. So there's a critical value at x equals 0. Third, x equals 0 will break your number line into 2 spaces. On the left of 0, so from negative infinity up to 0, and then to the right, then we'll analyze g prime in both. So interval A and interval B, the test value on the left of 0, negative 1, test value to the right, positive 1, plugging into the derivative gives me plus plus, so no change in sign. So this would mean g is increasing because the derivative is positive, still increasing because it's positive, So there is no max or min because it doesn't switch. So there's no extrema for this function. So that is a possibility. All right, so if you graph this function with your calculator, it looks like this. Decrease. Notice the derivative does not exist right here because it's a vertical tangent line, but then it continues to decrease. So there's no max or min. So you could have just a max, not a min, just a min, not a max. You could have both, you could have none. So it's all about what the derivative rules tell you. All right, this one, we're just going to do one more here. Find any relative extrema and sketch the graph. I just want to look at this one because finding the derivative of this one's a little harder. All the other ones we've just had to use our power rule basically. This one though we need a product rule. All right, so we got to find g prime. So recognizing that the product rule is necessary here because we have a product of a function times another function that both involve x. So the first function, x squared times the derivative of the second. So this derivative is e to the power. So e to the negative x, but times the derivative of the exponent is where this -1 comes in. So it's e to the power times the derivative of the power. So that's the first function times the derivative of the second plus, this time we take the derivative of the first, that's the 2x, times the second function. So you got to recognize that that's necessary and know how to do it. Then you've got to clean it up. So they factored out a factor of x and an e to the negative x. So that would leave right here, if I took out the e to the negative x and an x, I have a negative x left, so that's this part of it. And then if I took out an x, e to the negative x, there's a 2 left. So you could have negative x plus 2, they've just rearranged that to be 2 minus x. All right, next we need to find where this is 0 or where it doesn't exist. Since g prime can be evaluated for any real number, so there's no doesn't exist values, it's only going to come from setting it to 0. So if I set that to 0, we'll be setting each factor to 0. This factor, if I set to 0, there's no solutions. It's always a positive number. So the only critical values we're going to get are 0 and 2. When x is 0 or when x is 2, that will make these factors 0. This will never be a 0. All right. So 0 and 2, so we use those to divide up our x-axis. On the left of 0, in between 0 and 2, and to the right of 2. And this is what your chart would look like. Negative infinity to 0, 0 to 2, 2 to infinity. Pick a test value in each space. Plug into the derivative, this test value, see what you get. This gives me less than 0, meaning negative, so we'll be decreasing here. Plugging in a 1 to the derivative is greater than 0, meaning plus, increasing function, and then plugging in 3 into the derivative, less than 0 would mean negative, meaning that your function is decreasing. So by the first derivative test, the change in signs from negative to positive indicates minimum. That occurs at 0, while the change in sign from positive to negative indicates max, right? Negative to positive means decrease to increase, has to be a min. Positive to negative means increase to decrease, that would have to be a max. So to find the ordered pairs, you plug back into the function. So g of 0 simplifies to 0, so 0, 0 is a relative min. Plug 2 back into the function, gives you 4 e to the negative 2, so 2 comma 4 e to the negative 2 would be a relative max. And they've just shown a table from the calculator and then the graph. So again, I would just plug into your calculator, adjust your window just to make sure you can kind of see that your points make sense. When you're doing the homework in my math lab, I believe your graphing part will be multiple choice. So it's just a lot quicker to create those graphs using your graphing calculator. All right, so kind of this is a long section. So the summary shows you what it means for a function to be increasing, meaning the slope of the tangent line is positive. What it means for the function to be decreasing, meaning that the slope of the tangent line is negative. I'm not going to read all that to you. It's just more of a matter of can you visually identify that. So using the first derivative, a function is increasing If the first derivative is positive, a function is decreasing. If the first derivative is negative. A critical value is a number in the domain for which the derivative equals 0 or the derivative does not exist. In the ordered pair, CF of C is called a critical point. And then a relative max point is higher than all other points in an interval containing it, and a relative min is lower than all the other points in an interval containing it. The y value of such a point is called a relative max or min, if you plug those into the function. And then minimum and maximum points are collectively called extrema. So when they say find all relative extrema, they're talking about both. And then critical values are candidates for possible extrema. They don't have to lead to one, but they're the only places that you need to check. And then you use the first derivative test to classify as a max, a min, or neither. All right, there's a lot of stuff to learn in this first section that's going to carry over through the rest of chapter 3. So this will, you will need to spend some time thinking through these problems because they are lengthy. All right, that is the end of section 3.1.